Now there's one other thing that we sometimes talk about with linear approximation, which is this notion of differentials. What we did in the previous example was we approximated the value of some sort of function of interest to us at a specific point via the tangent line. But sometimes that's not exactly what we want. Sometimes it's more important to us to get an idea for just how a dependent variable is changing as we make a small change to an independent variable. So for a simple example, if we had a really nice relationship between a dependent variable y and an independent variable x, such as y is equal to 3 times x, we would intuitively know that if we changed x by a small amount, that we would expect y to change about 3 times as much. That's a really simple and straightforward relationship between a dependent variable and an independent variable, but as the equations relating those variables become more complicated, it becomes more difficult to make these types of estimates off the top of our head for how much that dependent variable will change. But the idea behind linear approximations and derivatives can help us make those estimations here. Now for our last example, we'll be using this idea of pizza, just because it's a fun thing for college kids to consider, which is when we have pizzas advertised to us from pizza chains, we are often given information about the diameter of that pizza. Is it 12 inches, 16 inches, 20 inches? And really what's important to us as consumers is probably how much pizza is there, and maybe as college students, how much that actually costs. So we're going to study that idea over the next 2 examples. The example we're going to work out in detail is, we've just seen these nice and common diameters of pizzas that are often offered in the United States. They're normally an even number of inches, anywhere from 8 to 16 to 20 even. What we want to think about is, as the size of the diameter of the pizza increases, in what way is that affecting the area of the pizza? Well, the first place we want to begin is we want to think about the way in which the area is a dependent variable of the diameter of the pizza. Here we're going to be using the variable L for maybe a length to denote the diameter of the pizza, because with derivatives it's really dangerous to use the letter D as your independent variable. So if we think of L as the diameter of the pizza, we can discuss the relationship between the area and the diameter. We more commonly think of the area of a circle as a function of the radius, which is half the diameter. So if we thought of the area of the pizza as pi times the radius squared, that relates to our diameter as pi times the quantity L over 2, all squared. In terms of contexts of rates of change, we think of something like dAdL as representing the rate at which the area of the pizza is changing as the diameter changes. If we move forward and compute this quantity dAdL, we have to come up here by A and remember to use the chain rule. So we'll get a dAdL on the left-hand side of this equation. By our power rule, this 2 will come down and multiply by the pi. The inside of the parentheses, the L over 2, will remain the same, and we'll subtract 1 from the exponent, and a 2 minus a 1 will be a raised to the first power here. However, we have to remember our chain rule and multiply by the derivative of what's inside the parentheses, and the derivative of L over 2 here is going to give me a 1/2. So altogether, my dAdL will be equal to 2 pi times L over 2 times a 1/2, and the 2 that we brought down and the 1/2 we have over here are going to cancel away. So altogether, that leads us to this equation for the derivative dAdL as pi over 2 times L. And what we really want to focus on is the change to the area as a function of the change to the diameter. So if we think about rearranging this equation and kind of putting the dl over on the other side, we can come up with this new equation that explicitly writes down what the change to the area is going to be in this situation as pi over 2 times L times dl. If we think of the derivative in this way, we can very easily approximate the change to the area of the pizza for specific L values and dl values. In particular, if we want to think about what happens when we have a pizza that's 8 inches in diameter, and we want to make a change of 1 inch to the diameter of the pizza, going from an 8-inch pizza to a 9-inch pizza, we want to know how that kind of change would affect the area. Here, we just plug everything in. By this relationship, the change to the area should be pi over 2 times 8 times 1, or in other words, about 4 pi. Putting that into terms that are particularly meaningful to us, this means that adding just 1 square inch to the diameter of the pizza results in 12.5 more square inches of pizza. And that's about 2 slices worth of pizza on an 8-inch pizza. So adding just 1 inch to the diameter of the pizza gives us about 2 more slices for these particular values. Now, as an exercise and a homework assignment for you if you're watching along from my class, I want to use the same sort of idea, but I want to talk about the cost of the pizza instead as a function of the diameter of the pizza. So let's imagine that when we are talking about pizza diameters anywhere from 8 to 35 inches, the cost of the pizza is given by this equation. We showed a 16-inch pizza having a cost of roughly $12, and the pizza company right now offered a large, which was a 16-inch pizza, and a giant pizza, which was a 20-inch pizza. The question we want to answer is, if this particular pizza company was to create a new pizza with an 18-inch diameter, so somewhere in between the 16-inch pizza and the 20-inch pizza, via the thinking of the previous slide, what's the approximate change we would expect to see in the cost function of this pizza? Where this cost function is really just modeling the cost of the pizza, presumably our company would round to more reasonable values that are normally charged for a pizza if the input value that we use for L here gives us some particularly funny outputs. So that's the question that we want to answer. Given that a 16-inch pizza costs $12 and we want to change the diameter of the pizza by 2 inches, what is the approximate change we would expect to see in the cost of the pizza, given that the cost of the pizza is modeled by this function?